Okay, we continue. In this part, we are going to do a comparison. We are going to compare the products we have just talked about in the previous parts. The GraceHopper Superchip, the MI300A APU, and then the MI250X GPU. So I put these three systems in the same table for the comparison. In the previous part, we have discussed that with the Superchip and with the APU from AMD, the MI300A, the programmer, they don't need anymore to do the data copy in, copy out from the host to the GPU. This is going to make their life easier because they are going to save quite a number of line of codes. They can spend more of their time to focus on the useful part. I mean, for their programming, for their application. So it has made their life easier. But we need to dive into a little bit in the architectural advancements. Why this has been done, how this has been done, what's the architectural advancements that have made their life easier. So let's start. We have a look at the system. The first thing I want to have a look is the GPU status. What's the status of the GPU? So for Superchip, for GraceHopper Superchip, and also the same for Grace Blackwell Superchip, the Hopper, the GPU, is connected to the host by the NVLink C2C. The NVLink C2C, but actually, if you look at the protocols that run on top of this NVLink C2C, that's the PCIe generation 5. So what I can claim is that because it's still connected to the host by using the PCIe protocol. So what I'm saying is that the GPU is still a PCIe equipment, even though it's connected to the host by the NVLink C2C instead of the PCIe link, the traditional PCIe link. So is still a PCIe equipment, is still a discrete GPU, a PCIe equipment. It's a coprocessor. That's their function. It's a coprocessor to the CPU. Now we move to MI250X. Is connected to the host by Infinity Fabric. Is still discrete GPU, but it is connected to the system by the Infinity Fabric. Okay, so by function is the same. It's a coprocessor, but it's not. It's a kind of PCIe equipment, but it's not really a PCIe equipment. It's more a coprocessor of the CPU, but connected to the host by the Infinity Fabric. It's different from the PCIe. It's not a PCIe equipment. It's really connected to the host, to the CPU by the Infinity Fabric, and there are the links that's not the same kind of link for connecting to a PCIe equipment. So it's no more a peripheral equipment. It's a kind of a discrete coprocessor, but connected to the system. Logically, you can think it's part of the system. This is in between the GraceHopper and MI300A. For MI300A, things are very clear. This GPU here, they are no more PCIe equipment because they are not connected to the system by any kind of links. They are directly integrated in the very center of the chip. Here it is. You have the 6 XCDs, the 6 GPUs. They are connected to the SoC bus, system on chip, they are connected to the system on chip bus, actually, which is an Infinity Fabric link. They are connected to the Infinity Fabric the same way as the CPU, as the CCD. This is the CPU, this is the GPU. So right now, the GPU is connected. The GPU is connected to the system system bus the same way as the CPU. So definitely it's not anymore an PCIe equipment. It's a processor. It's a coprocessor, but this coprocessor is no more connected by any link to the host. It's directly in the very center of the host. So if CPU and the GPU they are collectively called XPU. So this is the XPU. That's part of the system. And the reason for me to put this MI250X in this table to do the comparison is that MI250X is a little bit strange. If you look at these links, this kind of thing, basically you will think that this is kind of more like the PCIe equipment. It's connected to the system, to the CPU by Infinity Fabric links. But logically, we are going to find out that MI250X is more like MI300A. It's like a kind of discrete MI300A, and the same idea comes from also from AMD. Basically, AMD is taking this MI250X as the earlier generation of products for MI300A. So that's the reason I also put this MI250X in this comparison table. So this is the GPU status. We have the GPU as the PCIe equipment. We have the GPU in the very center of the chip, is part of the processing units. And then we have in between, we have this MI250X. Let's continue. So if the system is connected to the host as a PCIe equipment for the GraceHopper, here we have this NVLink C2C, which is the low layer connection. But on top of this NVLink, the protocol is a PCIe equipment, is the PCIe generation 5. So this logically and also physically, no, pretty much logically, because they are connected to the system by the PCIe protocol. So pretty much it's more a PCIe equipment. But here the connection for the GPU to the CPU for MI250X is the XGMI protocol. Is XGMI over Infinity Fabric. If you think that Infinity Fabric is the low layer connection, and on top of that, what you have is this XGMI protocol. XGMI stands for External Global Memory Interconnect. So this is the connection between the CPU and the GPU. And later on, we are going to find out that the CPU and the GPU can access each other's memory by using this protocol. And that's the reason why I'm saying it's more like a discrete coprocessor, but it has not been integrated on the chip, on the same chip as the CPU, as the same way as MI300A. That's the earlier products the earlier generation of products for MI300A. Okay, so I just want to mention that on top of this NVLink Z2C, besides this PCIe protocol, there is also this the ATS, the extended ATS service. So it's ATS basically is part of the PCIe protocol, but this is kind of extended ATS service. So on top of this NVLink, you have these two stuff. But because the fact is that for MI300A, because the GPU is directly in the center, in the very center of the chip, it's an XPU. It's no more a discrete GPU. It's no more a PCIe equipment. So there is it's directly in the center of the system. So there is no link between this GPU and the chip, the system, the host, because it's already inside the very center of the host. Okay, now we need to have a look of this cache coherency. The cache coherency for GraceHopper and Grace Blackwell is AMBA-CHI. AMBA-CHI is advanced microcontroller bus architecture coherent hub interface. So this is the cache coherence protocol from ARM. Because this one you have this Grace CPU, this is the ARM CPU, but have the license from ARM. Nvidia has also got the license to use this protocol on top of this NVLink C2C connection, because the Hopper GPU need to be cache coherent with the CPU, and naturally you have this cache coherent protocol from ARM. You have the license. You put that on the system, and you have it run on the NVLink C2C, and this is the way for Nvidia to make it work. So it has this kind of cache coherent protocol to guarantee that the GPU and the CPU's cache will be coherent. So this is the cache coherency. But here for MI250X, the fact is that there is no cache coherency. So the Infinity Fabric interconnect supports zero copy memory access. So where any processor in the system, the CPU, the GPU can access each other's physical memory directly over the interconnect without the need to maintain a local copy. That means they don't need to maintain a local copy. Basically, if you have a local copy, that should be in the cache. If they have no cache, there is no cache coherency. So this is with MI250X. It is connected to the system, to the CPU by the Infinity Fabric, by the XGMI protocol, but there is no cache coherency protocol running on top of this Infinity Fabric. Now, I just want to mention here is that basically, if you look at this Infinity Fabric and the XGMI protocol between two CPUs, you have the cache coherency protocol running on top if you have a dual socket system. But this one is a single socket system, as most importantly is that the CPU to connect to the MI250X GPU, the CPU is 7853, and this one uses the same core as Milan, but its code name is Trento. So it's a CPU specifically designed for Frontier, for the Frontier system to be connected to the MI250X. This may explain why there is no cache coherency running on top of this system. Okay. Now we will move to MI300A. For MI300A, the cache coherency is everywhere. So the CPUs are hardware coherent with all CPUs and GPUs using the same type of probe filter-based coherence protocol as in EPIC CPU. So if you have dual socket system, you have two CPUs, the two CPUs will be cache coherent. And here, all the CPUs and all the GPUs, they are going to run the same kind of cache coherency protocol to guarantee all of them are cache coherent. Okay, that's between CPU and the GPUs. Okay, then between all the CPU and all the GPUs inside a socket, that means between all the CPUs and the GPUs on a single MI300A chip. Okay, but the other fact is that GPU are software coherent to GPUs in other sockets. Okay, each socket you have an MI300A APU. So the other, if you have 4 APUs in your system, you have 4 sockets. The GPUs are software coherent to GPUs in other socket. The reason to have this is to reduce hardware coherence bandwidth needs. And the software coherent and within a socket, you have, let's see here, we have 6 XCDs, means you have 6 GPUs. For these 6 GPUs, you have directory-based hardware coherent within a socket. Okay? Using a slightly simpler protocol than the CPUs. Basically, they are running the same kind of protocol as the CPUs, but they are simpler. They are more simpler. Okay, so this is the cache coherency for the processor side cache. And for this MI300A system, there is specific element. I mean, there is this infinity cache, a new component, which is a memory side cache. Because it's a memory side cache, so it's not need to be participate in the coherence transaction. So it's not coherent with the others. It's a memory side cache. So these are the difference regarding the GPU status, regarding the link between the GPU and their host, and regarding the cache coherency. Okay. So these are the hardware level differences. Now let's move on to the memory hierarchy. For the GraceHopper superchip and for the Grace Blackwell, for these kind of systems, you have the NVLink, you have 18 NVLinks, and you have the two processors, the CPU, and the GPU connected to each other. Okay, but the fact is that if you look at this kind of system, even for superchip, the CPU has its own memory. For Grace, is the LPDDR5X, this is the memory, and for GPU is the HBM3, this is the memory, and the memory belongs separately to the CPU and to the GPU. So for each superchip, you have 2 parts. One part consists of the Grace CPU with the memory. The other part consists the Hopper GPU and the HBM memory. So you have the two parts basically we can see that you have two subsystems that are connected each other by the NVLink. So this is the system, and then you have these two types of memory, and this is the two types of memory and the memory hierarchy. You have also this cache for GPU, and also you have the cache for the CPU. So you have the separate memory hierarchy for CPU and for GPU. Okay. It's a little bit interesting for the MI250X. In the previous page, we have mentioned that MI250X, there is no cache coherency. The CPU and the GPU accelerator components share a flat physical memory space. So they share a flat physical memory space. Any processor can directly access the HBM in any of the 4 accelerators, and all of the DDR4 connected to the CPU. So the fact is that with this MI250X, the GPU, the CPU, both of them can access all the memory. All the memory. The CPU can access the memory of the GPU can access the memory of the CPU, and is by going through this infinity fabric, this link. Okay. But there is something very interesting is that if you do a memory allocation, the memory allocations can be configured as coherent. When a GPU modifies CPU memory that's marked as coherent, changes are immediately reflected on the CPU side. On MI250X, to achieve this effect, GPU side caching is disabled for coherent memory access. So that's the reason why I'm saying that there's no cache coherency. The GPU cache has been disabled. So the GPU can access the CPU's memory, the CPU can access the GPU's memory, just directly go through this infinity fabric. There's no cache coherency. So each access to data located in remote or coherent memory generates traffic over the CPU-GPU interconnect. This is the fact for MI250. While the use of coherent memory is generally detrimental to performance, but it simplifies programming for application with complex access patterns. So here we have an example is that if you have CPU and GPU kernels operating on the same data, this is going to make this kind of arrangement of the direct memory access without cache is going to make their life easier. Okay. So this is MI250X. Now we move to MI300A. MI300A, things are totally different. The memory, is no more like the super chip. You have two parts. You have the CPU, you have the GPU, you have the CPU memory, you have the GPU memory, and you have the CPU cache, you have the GPU cache. Actually, you have two hierarchies. You have two you have two hierarchies for this GraceHopper. But for MI300A, there is only one hierarchy. There is only one memory system. That's the HBM memory. Now, it's unified. It's called unified memory by AMD. But we just need to be careful because unified memory has been used by Nvidia, by CUDA. That means something else. But here for For MI300A, the unified memory means it's really unified. It's hardware and software unified. Now, is you have only one kind of memory, which is HBM3, and it is unified and shared between the GPU and the GPU. So you don't have two memory hierarchies. You have only one set of memory, which is using the HBM, and it is shared by the CPU and the GPU. This dramatically reducing the latency and improving the communication throughput. This also pays dividends at the system level by eliminating the interconnect and also the DDR memory. So DDR memory no more, you have only HBM memory. You remove the DDR memory from the host, from the CPU, and then you share this as HBM memory for the CPU and the GPU. The CCD means CPU, XCD means GPU. The CPU and the GPU share a unified HBM-based memory system. This enables direct low-store access to the HBM by either type of processor without any data copying, as it's typically required in systems that use discrete GPUs with their own video memory distinct from the whole CPU memory. Because you have these two kinds of memory, and if the CPU has to access GPU memory, it has to copy the data from the memory into its cache. And the local copy, you understand, basically you understand this is the local cache. And the GPU, if it has to access the CPU memory, it has to keep a copy in its local cache. So you have to do this kind of cache coherence. Just because you have two sets of memory hierarchy, but for the MI300A, because you have only one memory hierarchy, so you don't have this kind of cache traffic that originates from the fact that you have two memory hierarchies. You won't have this kind of cache coherence traffic on the system. The CPU can initialize memory and then directly launch a kernel on the GPU components. So because it's the memory is shared by the CPU and the GPU. If you remember that for the traditional systems, we have to copy the data from the host to the GPU for the GPU to work on that. But because right now everything has been unified, you have prepared data. You don't need to copy out the data from the host to the GPU, because it's already in the shared memory. You just ask GPU to work on this piece of data, and the job can be done. That means for MI300A, there is no programming distinction between GPU and CPU and GPU memory spaces. You have only one. As I said, you have only one memory hierarchy. Okay. And a single process can access all memory compute elements on socket. So each process can access everything from the same socket. So the memory hierarchy part, we see the difference between the three systems. Really is that for GraceHopper, you have two hierarchies, and you have one memory hierarchy for the MI300A, and for MI250X is a little bit different than the two others. Each one can access the memory of the others, but without the cache, without using the cache. So this is the memory hierarchy. So we had look of this cache, and we had look of this memory hierarchy. Now we need to have a look of this unified virtual memory or shared virtual memory. So this is a topic a little bit difficult to understand and to explain, but let me give it a try. Is that even before the MI300A APU, before the GraceHopper superchip, when the GPUs are connected, when the GPUs are still connected to the system, to the x86 CPU, by using these PCIe links, actually to have your application work, to make the programmer's life easier, we already have this kind of unified virtual memory from Nvidia and shared virtual memory from AMD. Now they use different names, but basically that's the same thing. The fact is that when the GPUs were still connected to the systems separately, the old products before this MI300A and this GraceHopper, the super chip, the GPUs were always connected to the host by using the PCIe link, and that makes the fact that you have two memory hierarchies, just like this one. Now, from the point of view of memory hierarchy is the same. You have two memory hierarchies. You have one memory hierarchy, that's the CPU part. You have another memory hierarchy, which is the GPU part. At hardware level, cache level, you have two memory hierarchies. But to make life easier for the programmer, in the early days, we have already this kind of unified virtual memory or unified virtual addressing from Nvidia, from CUDA available. That was a software solution. You have this unified virtual memory. The reason for us to have this unified virtual memory is that because if you have your application will have two parts. One part will be run on the host, the other part will be run on the GPU. And the part run on the CPU and the part run on the GPU, they are going to have two virtual address spaces. So one is the CPU virtual address space. The other one will be the GPU virtual address space if you don't have this link, or the link is PCIe. You have two virtual address spaces, but basically for an application, there must be the communication between the two virtual address spaces. How to make that happen? There was already a software solution from Nvidia. That's by the CUDA programming platform, or the CUDA runtime. So it supports this kind of unified virtual memory. Basically, the idea is that you have to make the two virtual address space communicate each other, and the best way to make this happen is to make these two virtual address spaces a unified one. So it's called unified virtual memory or unified virtual addressing. Basically, you need to make this happen. And this this was with the traditional x86 GPU connected to the x86 CPU connected to the GPU by using PCIe. With the advancement of this GraceHopper superchip, there is still the need to make this to give the programmer this kind of unified virtual address space. So what we are going to do here by Nvidia is that Nvidia has let's see, they has deployed this kind of ATS service. They have extended this PCIe protocol. They have deployed this ATS service, and they have got this kind of cache coherency between the CPU and the GPU by this AMBA CHI protocol. All these hardware mechanisms are going to help to realize this virtual address space, the unified virtual address space. And we are going to have a look at this one. We are back to the link between this one and this one, which is the C2C link. You have this kind of link. So memory allocation are device specific and live in separate host and GPU memory spaces. In traditional x86 plus PCIe GPU systems, memory transfers between the CPU and the GPU address space requires the utilization of specific copy APIs like CUDA, memory copy. If you still remember, in Section 1, in Section 3 and Section 4, I have mentioned that you have to do this memory copy because the GPU cannot access the CPU's memory, and it is up to GraceHopper and MI300. The programmers, they don't need to do the copy and the copy out because the following. Because unified virtual address simplifies this by enabling devices, GPUs, to share a unified address space with the host CPU, allowing every PU, CPU, and GPU on the system to access memory using the same pointers. So here, exactly this is the picture which shows what has happened is that with all this kind of support, all this kind of support from all these hardware mechanisms, and right now the unified virtual addressing is more easier to deploy and is supported by Nvidia, GraceHopper, and Grace Blackwell. In GraceHopper system, a single page table. Right now, you don't have any more two separate page tables. You have a single page table and virtual address space shared between CPU and the GPU. Now, to have this happen, a specific unit called Address Translation Service Translation Buffer Unit. So ATS TBU, which is Address Translation Service Translation Buffer Unit, is implemented to provide fast translation and support interaction between all MMUs and TLBs on the system. Basically, you have two MMUs. You have one CPU MMU, you have one GPU MMU, and then you have this virtual address space. If you have to read the data from the memory, you have to translate this virtual address into physical address, and the page table, which is the table you need to look up to do the translation. And after it has been translated, it could be translated into GPU memory or into CPU memory after it has been translated. And the CPU or the GPU can use the translated physical address to read the data located in that physical address. physical place and read data. So this is the way for Nvidia to realize this kind of unified virtual memory. Okay, so now we move to MI250X. For MI250X, for AMD, it's not called unified virtual memory, it's called shared virtual memory. The implementation is different from the Nvidia one, but at the end you have the same effect. Is that it seems from the programmer's point of view, you have one shared virtual memory between the GPU and the GPU. How does that work? We won't dive into the technical details. Basically, is that you have a GPU memory manager, you have kernel side, you have the memory management unit, not memory manager, memory management unit. is memory management unit. You have a kernel heterogeneous memory management unit and the memory management unit. And you have GPU side memory management unit. And you are going to have two separate page tables for GPU and for CPU. This is the CPU, this is the GPU. And what AMD has chosen to do, have chosen to do is, it has this kind of shared virtual memory driver, and this driver is going to be on the host side, and it is going to be the link between the two page tables. So from the programmer's point of view, you are going to have a unified virtual memory. Now, this is not the right word for AMD system. What I'm trying to say that you are going to have a shared virtual memory between the CPU and the GPU. And it's shared, and everybody, the CPU, both the CPU and the GPU will use this shared virtual memory and the page table to do the virtual address to physical address translation. But be careful here is that it has two page tables. You have one side for GPU, the other side for CPU. You have two page tables because you have two memory hierarchy, and this SVM is going to be the one which lives in between the two page tables and makes and present to the programmer, give the programmer the view of only one shared virtual memory. This is what SVM is doing, and this one gives the programmer the point, the feeling that you have only one page table. Basically, you have two. Okay. So SVM manages the unified memory space by ranges rather than pages in host and device memory domains. So this we won't dive into the details, but here for Nvidia, they manage this page table by pages, and here the page table is managed by ranges. Range is multiple pages, multiple web pages. So okay, AMD's shared virtual memory has a distinct design from UVM from Nvidia, where both are implemented as software driver mirroring page tables on both the host and the device. SVM interfaces with the Linux kernel's heterogeneous memory management, which is designed for broader hardware compatibility and integration, while HMM is still in development. Its unified framework is poised to greatly simplify driver development and enhance application portability. Okay, so the key point is that for the programmer, there must be a unified virtual memory space or shared virtual memory. Okay, that means from the programmer's point of view, they help to get this kind of presentation that the two page tables are logically just one page table. The programmer, maybe they don't care how it's implemented, but from their point of view, it seems that they have only one page table, either a shared page table, a shared virtual memory, or like this one, an integrated page table that's accessible by the two. That's the virtual memory part for this one. Now we move to MI300A. MI300A presents a single unified memory, including cache coherency between CPU and GPU to the CPU cores and GPUs, which simplifies programming model. Now we need to understand this way. This unified memory here really means physically unified memory and logically unified memory for sure. So now this is the thing that has been worked out by AMD for MI300A is quite different from the two others. Now it's a unified memory including the cache coherency and between the CPU and the GPU, everything is unified. We have seen this one because basically you have only one memory hierarchy. So it's physically unified. And then in the system, you are going to have one page table, one translation service from the virtual address to the hardware address. Because you have only one memory hierarchy, you don't have two. You don't need to manage two. You have only one. Things are so much simple. You have only one unified physical memory. You have only one memory, or you have only one virtual memory virtual memory space, and you have only one virtual memory to physical memory translation mechanism, which is the page table. Okay, a unified memory enables eliminating redundant data copies, removing the distinction between host and device memory spaces. So you have only one hierarchy rather than two, and it enables fine-grained sharing between processing elements. So it's saying that Nvidia provides a kind of unified memory to the software by using page migration to transparently copy data between the CPU, DDR, and the GPU's HBM memory. So basically, you have a kind of a unified memory, which by the CUDA, but basically, but the CUDA runtime is going to do the page migration between the CPU DDR and the GPU HBM, and then it can still give you a sense of unified virtual memory. This is what NVIDIA did. So, but here the MI300A avoids such data movement overheads by matching the actual physical memory organization with the programmer's will. So the programmer's will is that I have a unified virtual memory address. I have a unified memory space. I don't want to care what's the difference, either DDR or HBM. I don't want to care. And exactly MI300A gives the programmer this kind of will. You don't need to care DDR or HBM, because here you have only HBM. You have only one unified physical memory. You have only one unified virtual address space. You have only one page table for the virtual to physical address translation. So that has been simplified. Now, we discussed this kind of virtual memory address, virtual unified virtual memory or shared virtual memory. In this discussion, we have mentioned that the page migration. So we need to have a look at this page migration. So if from the programmer's point of view, I have a unified virtual memory, and but underneath this unified virtual memory space, there are two kinds of memory. There are the HPDDR memory, and there is this HBM memory. So basically, the programmer they don't want to care, but they have to care this kind of memory, because we have the difference of the bandwidth for these two kinds of memory. So the leaders the best situation is that if you have a GPU working on the data should be in the GPU's memory, in the HBM, because you are going to have a high bandwidth. If the CPU is working on this piece of data, the data should be in the CPU's memory, because you don't need to go through the NVLink C2C to access the memory. That's going to make things complicated, and you have to care also this cache coherency, this kind of problem. So this is what programmers want to have. But from Nvidia, there is this kind of mechanism, which is automatic delayed access counter-based migration. So the point is it's not too much complicated to understand. In order to improve performance of application which use system allocated memory, the GraceHopper system can be configured to automatically migrate memory regions between GPU and CPU physical memory. It's important to note that this migration is different and independent from auto-NUMA migration used in the Linux kernel. Thanks to the fully coherent GPU-CPU memory and direct memory access capability of GraceHopper, which comes pretty much from the ATS service, from the cache coherency protocol, plus the NVLink C2C link, which is a high bandwidth link. This automatic migration feature is purely aimed at enhancing performance and does not intend to overcome technical limitations. So this is purely for performance. It's not, I mean, if without these kind of features, the system works, but you are going to have maybe you are going to have a problem with performance. But this one is going to help you to increase the performance. The default migration strategy detailed in NVIDIA's open source GPU driver 1 relies on hardware counter to track GPU access to memory range. When a counter value exceeds a user-defined threshold by default 256, the GPU issues a notification in the form of a hardware interrupt, which is handled by the GPU driver on the CPU. The driver then determines whether to migrate the page belonging to the associated virtual memory region the intent of this strategy is to automatically migrate pages that are heavily accessed by the GPU from CPU memory to GPU memory, then improve performance. So as I said, this is a mechanism try to help to improve the performance. And it's very simple. If your GPU has tried to access the memory many times, you have done that more than 256 times, the system is going to believe that this piece of memory should be migrated to the GPU physical memory, and it's going to do that. It's going to decide to do that or not based on their algorithm. But this is how this page migration works for GraceHopper. Okay, for MI250X, when a GPU kernel accesses memory that's neither located in the GPU's physical memory nor mapped into GPU virtual memory, a page fault is triggered. MI250X system has the ability to resolve the page fault and retry the memory access. This feature, referred to as XNAC, can be enabled by setting the environment variable, this environment variable as 1. Additionally, users must ensure that the GPU kernels are built to match the system's XNAC configuration. So in that case, if this has been enabled, memory can be automatically migrated to GPU from CPU on a page fault if this one is set. You do need to explicitly migrate or provide managed memory. This is useful if you are migrating code from a programming model that relies on unified or managed memory. So if this is the case, you are going to benefit from this kind of setup. So if you set up this, then when the GPU is trying to access the memory, and if that's not in the GPU's fabric, if it's not yet in the GPU's memory, if it's not in the GPU's virtual memory, and then the system is going to do the page migration and migrate the data to the GPU's physical memory. So that's going to also improve the performance for the application. And the last one for MI300A, oh, that's very simple because you have only one memory hierarchy. That means what? That means there's no need to do this page migration because you have only one memory hierarchy. You have only one unified virtual memory space. So you don't need to do that. Okay, we have gone through this table for the comparison of the three systems. Okay, so the short conclusion is that usually this the fact that MI300A has brought this GPU into the very center of the chip, it has the same status as the CPU. And because this has been done, you don't have the need to have two memory hierarchies. And then AMD has the possibility to design only one memory hierarchy for both CPU and GPU. Because it has the only one memory hierarchy, you don't have this problem with the unified virtual memory space and the page migration, etc., etc. Okay, so really, my personal point of view is that MI300A is is a product with a very important technical evolution or somehow a technical revolution, if that's not a too big word for this MI300A, but it has some unique features that make it worth the value, that make it worth trying to use, and that's the key message from this table. And before MI300A has been published, we have this MI250X. The MI250X, that's in between the GraceHopper and the MI300A. I mean, if you look at this architecture, it's in between the two, but it's more like MI300A because even though the MI250X is a discrete GPU, its memory has been unified with the CPU memory by this infinity fabric link. And even though there's kind of an infinity fabric link without cache coherency, but it's already unified. So this is really the previous generation before MI300A. Logically speaking, I mean, if you look at this logical architecture, that's really the generation before MI300A. So the last word about the GraceHopper and the Grace Blackwell, we have also very important technical evolution. Even though it's still a PCIe equipment, but it has been enhanced. What I mean is that the GPU has cache coherency with the CPU. The GPU and the CPU's virtual address space has been unified. And then the CPU, basically the CPU and the GPU from the programmer's point of view, if you don't want to distinguish the two kinds of memories, you don't need to do that. It's already there, and you also have this kind of automatic page migration that is going to help the programmer to improve their application's performance. So that's also a very important product from the marketplace. Even though personally I love more this MI300A, this architecture and this solution. So this is the summary of the three products. Basically, from the users, from the programmer's point of view, we have discussed in part 1, part 2, and part 3, is that from the programmer's point of view, the benefit is that you don't need to care about this from host to CPU from host to GPU data copy in, copy out. You don't need to care about that because the memory system, the memory, the virtual memory has been unified. So it can be done without this data copy in, copy out. So this is programmers' point of view, is their benefits. But underneath this benefit for the programmers, underneath the implementation of this kind of benefit for the programmer comes from very, very different architectural evolutions. So we have one side from MI300A, they have brought this GPU into the very center of the chip, and they have just one memory architecture. And we have the same time from Nvidia, they have still they have still this GPU connected to the host as a PCIe equipment, but they have advanced this connection between CPU and the GPU by using C2C link, which is bandwidth, and they have extended this PCIe link by having this ATS service and this memory cache coherency. So that that gives the programmer the same benefit, but underneath these programmers' benefit, the architectural difference are here from this table. So this is the for the comparison of these three products. We are going to have rest, and afterwards we are going to discuss some topic related with the GraceHopper and MI300 APU, and then we are going to summarize this section. So see you very soon.